薄木山
different assets and a range of different attacks. So far, we've identified 6 different attacks, releasing the message contents and traffic analysis, and 4 what we call active attacks. I think I didn't say the difference between passive and active. Maybe I should say it now. Passive attacks involve the attacker doing something that doesn't modify how the system works. The attacker is passive and they don't need to make changes to the traffic in the network. They don't need to send extra messages. They just sit there and listen. An active attack involves the attacker making some changes to how the system works. For example, they modify a message. They inject a new message. So the difference between those types of attacks, passive and active, is passive, the attacker does not modify how the system works. Active is the attacker does make some changes. The significance of comparing the two is that passive attacks are usually easy for the attacker to perform and hard to detect, whereas active attacks are easy to detect. So the approaches that we use to defeat those attacks, usually passive attacks we need to use techniques in advance to prevent them, whereas active attacks we use techniques to detect them. And we'll see that as we go through some cryptographic techniques. We also said that we can talk about inside or outside attacks, depending on who's doing the attack. We mentioned that there are countermeasures or security mechanisms. They are the techniques that we'll use to implement the security services. So they'll be the techniques to prevent, detect, recover from attacks. And prevention and detection in particular usually use cryptographic techniques, encryption especially. So the next topic we'll look at those cryptographic techniques. Am I finished? There's 2 more slides. I will not go through these. Most of the lecture topics I'll include 2 or 3 slides at the end, giving some other areas that you may explore if you're interested. You can explore on your own, like different organizations which are involved in computer security. And in some other slides you may see some future issues or research issues that can be considered. But we can discuss maybe outside the class if you're interested. A key part of providing security mechanisms is to use encryption, or in general cryptography, cryptographic techniques. So we want to talk about what is encryption especially, and what other techniques are used to implement our different security services. I think you've all heard of encryption. Some of you may have deliberately used it, maybe encrypted a file, and you indirectly use it, or you use it on a regular basis when you use a number of network protocols. HTTPS, for example, accessing a secure web server, encrypts your data before it's sent. So in this course, we'll not look at the details of how encryption algorithms work, but instead just say, well, what do we mean by encryption? List some of the different algorithms available, and present some of the trade-offs and types of attacks. Encryption is used for different security techniques. The key one, or I would avoid saying key, the important one is confidentiality. So let's start with that. How do we keep data secret? Encrypt that data. So our aim is to take our confidential information, our message, and make sure that unauthorized individuals cannot read that message. That's what data confidentiality is. The way that we do that is we take that confidential information, encrypt it, and we use an algorithm, an encryption algorithm, such that anyone can see the encrypted data. We don't care who sees the encrypted data, but the algorithm should be so that only authorized people can decrypt to find the original data. And the authorized people will be identified with the use of keys, secret keys, for example. Encryption is used for data confidentiality of information being sent across a network. We say sometimes in transit, the data is sent across a network, but also for data at rest, data stored on a disk, for example. So the same concepts are used. So I want to encrypt a file that's saved on my hard disk. I encrypt it, and I save the encrypted file on my hard disk. Anyone who accesses my hard disk cannot get the original file unless they have the key. Similar, I want to send data across a network. I encrypt it before I send it. Anyone who intercepts that message, like we did with Wi-Fi, can see the encrypted message but cannot decrypt it unless they have the key. The same approach is used whether it's saved on a disk or sent across a network. Most of the examples we'll use will be sending across a network. So a simple model is that we think there are 2 users, the 2 normal users, A and B. A wants to send a message to B, and A and B want this message to be confidential. That means that when A sends a message to B, we don't want anyone else in the world to be able to read that message except B. Of course, A can read the message they created. And for anyone else in the world, we'll represent as just one other user, an attacker, user C in this case. What we'll assume, so user A, their computing device, generates the message, and will send something to user B. We will assume that some other user, user C in this case, who's performing an attack, can intercept anything sent between A and B. Somehow they can intercept. Somehow maybe that they do the attack on the Wi-Fi link, or somehow maybe they simply go to the computer and get a copy of a file, or they tap into a wide link, or to get access to an intermediate device like a router. But the assumption is somehow the attacker can intercept anything sent between A and B. Therefore, we can't send the original message between A and B because it will not be confidential. So what we do is we encrypt the message before we send it. User A has the original message that they want to send to B. We refer to that message as plain text. It doesn't have to be text. It can be any format, but the name we give this original message is plain text. And what we do before we send that is we encrypt it. We apply an algorithm, an encryption algorithm, or a cipher, And it takes as an input the plaintext, and we use a key to encrypt. And the output of that algorithm is what we call the ciphertext. And it's the ciphertext that A sends to B. And the encryption algorithm will be chosen such that there's a corresponding decryption algorithm where when user B receives the ciphertext, they take that as input, they have a key, and they apply the decryption algorithm such that it will produce the original plaintext as output. That's the idea. So a couple of points on that normal process. The encryption and decryption algorithms used at A and B go together. That is, they're related. Sometimes they're even the same algorithm. They must have the property that if we encrypt the plaintext message to get ciphertext, if we decrypt that ciphertext using the correct key, we must get the original plaintext. So the algorithms must return the original plaintext. They cannot return something different, otherwise they don't work. And the algorithms take as an input a key. In this picture, I say that the encryption uses key 1 and decryption uses key 2. They may not be different keys. They may be the same values. So key 1 and key 2 may be the exact same value. In some schemes they are the same. In other schemes they are different. From the attacker's perspective, the attacker can intercept anything that A sends to B, in this case the ciphertext. The attacker wants to find the plaintext. That's their aim. They can easily obtain the ciphertext. If you have the ciphertext, you can try and decrypt that ciphertext. And this assumes that the attacker knows the algorithm used for encryption and decryption, and that will be a common assumption. The attacker knows how he did the encryption and decryption. So assuming the attacker knows the decryption algorithm and they know the ciphertext, what do they need to get the plaintext? What does the attacker need to get the plaintext? They need key, the key 2 in this case. Okay? So the important part here is that key 2 must be kept secret. If the attacker knows key 2 in this scheme, then they can decrypt very easily and get the plaintext. So we talk about secret keys. Keys are normally kept secret. In this case, user A and B may know the keys. So we talk about secret keys. Keys are normally kept secret. In this case, user A and B may know the keys. They cannot tell anyone else, otherwise this scheme fails. It's not secure. And later we'll talk about some different approaches of how to use secret keys. Even if the attacker doesn't know the key, it should be practically impossible for the attacker. And there are such algorithms that we consider secure, so we'll list some of them as we go through. So that's our general model for encryption. Encrypt the plaintext using one key, and the receiver decrypts the ciphertext using a potentially different key. It may be the same in most of the cases. Referred to as symmetric key encryption. Any questions yet? We have plenty of space in the front 2 rows. Symmetric key encryption involves using the same key at both sides. There's a single key. It's sometimes referred to as simply a secret key, a symmetric key, or a shared key. And that's one of the more common forms of encryption for confidentiality. We'll see another one later. So, for symmetric key encryption, we need a good algorithm. We say a strong encryption algorithm. An algorithm such that if the attacker knows that algorithm, and they know the ciphertext, they cannot get the key or plaintext. And we need that the sender and receiver know the key to be used, and that they keep that key secret. If someone else discovers the key, they can easily decrypt. In the study or the analysis that we do, we'll assume that the cipher, that is the algorithm used, is known by the attacker. So the algorithm used to encrypt and to decrypt is known by everyone. The reason we assume that is it's usually easy for the attacker to find that even if they don't know it. And for example, the algorithm may be implemented in your operating system. And everyone knows, you can guess which operating system the users are using. It doesn't take much to find out what algorithm they use to encrypt. So normally the cipher is assumed to be known. And at this stage we'll assume that the keys used by user A and B are known by A and B and not known by anyone else. That is, they were distributed in a secure manner. That becomes a bit of an issue which will arise when we look at key management. How do we get the key from B? At this stage we'll assume that B knows the key that A is using. So what algorithms are used for encryption? How do they work? And again, in this course we'll not go into the details of those algorithms. We'll touch upon the principles and list some of the algorithms, but not look at their designs. But basically encryption uses 2 main operations: substitution and transposition. And they're very simple. Substitution is you replace one character, one element, with some other element. And we'll show a very quick example if we use the English language as our alphabet. And the example of substitution is you have a word you want to encrypt, then you replace one letter, the letter S, with some other letter in the alphabet. And the algorithm defines which letter you replace it with. So that's the operation of substitution. And transposition is just rearranging elements. For example, you have the letters S, T, E, V, E is the word you want to encrypt. Transposition is an operation that says rearrange those 5 letters. So maybe you get T, E, V, S, E. That's a transposition operation. And most ciphers used today, symmetric key ciphers, use a combination of substitution and transposition operations. But they don't just do a single substitution or a single transposition, they use multiple steps, a substitution, a transposition, and then repeat multiple stages, and they refer to as product systems. Let's give an example of those 2 operations. Very simple ciphers, not secure, but easy to demonstrate. The first one is the Caesar cipher. And the Caesar cipher is maybe 2,000 years old, and the general approach is that we take, let's say we're using English language as the English alphabet. Now all of our plain text messages contain characters from A to Z, and let's keep it as lowercase only. Then when we have a plain text message with the Caesar cipher, to encrypt it, we take each character in the plain text message and shift it K positions to the right, where K is the key. And that will produce our ciphertext. So a quick example. Everyone seems to be awake and listening, so I'll start with hard examples. Let's skip the simple ones. Instead of giving you an encryption, I'll give you a way to decrypt. Let's say I give you some ciphertext. And here it is. Here's the ciphertext. And I give you the key. The value of the key, K, is 3. In the Caesar cipher, and the algorithm or the cipher we're using, there are different ciphers. In this case, we're using what's called the Caesar cipher. The Caesar cipher, to encrypt, takes each letter and shifts 3 positions to the right when we use a key of 3. If the key was 4, it would shift 4 positions to the right. Shifting to the right means if you start with the letter A, shift 3 positions to the right, A to B, to C, to D. If you encrypt the letter A, the ciphertext will be the letter D. Decryption should return the original plaintext. Decrypt our ciphertext. Decrypt it, not encrypt in this case, because I think you'll find encryption is easy. Everyone told me the quizzes were easy yesterday, so we'll start with the hard ones. Decrypt that ciphertext. Find out what the plaintext is. C, I use as a shortcut for this ciphertext. K is the key, so what's the plaintext? B. Anyone have the answer? Yep. How do you get the answer? Shift to the left to decrypt. If we encrypt plaintext, we say we shift to the right 3 positions. To get the original plaintext back, we take the ciphertext and shift 3 positions to the left. So take the first ciphertext letter, V, and then in the alphabet, you need to remember the English alphabet, go back 3 positions. What's 3 positions before V? I'll make it easier for you. There's the alphabet numbered, maybe a little bit easier. So if we have V, go back 3 positions. S. So the first letter of plaintext is S. We substitute one letter with another. So this is a substitution operation. And the rule for which letter do we substitute with is, well, 3 positions to the right to encrypt. And to decrypt is the opposite.
なんて怖いんだ。スズメバチじゃないの。スズメバチじゃないの。なんて怖いんだ。こんなとこまで。スズメバチに遭遇しました。
Same key in this case, 3. You'll get plain text that makes sense, that we can recognize. But if you decrypt that ciphertext with the wrong key, it is the wrong key because I actually encrypted using the value of 3. If we use a key of 4, we'll get a plaintext value which doesn't make sense. And we'll be able to recognize that. The attacker or the user will be able to recognize something went wrong here. I got ciphertext, I decrypted with key 4, I get a plaintext message that doesn't make sense. So I know someone who encrypts a plaintext message will start with a sensible plaintext message. That'll be a principle that comes up. Decrypting with the wrong key gives, we'll say, random characters and can be recognized as being incorrect. So that's an example of a substitution cipher. Any questions? The purpose of this example is not for you to really remember the Caesar cipher. The details are not important, but just to know that, right, this is a substitution. A transposition is when we rearrange letters. We don't replace them from something in the alphabet, we just move them around. That is, we take the plaintext and move the letters inside the plaintext. And a simple one that we use quickly is called the railfan cipher, where we have a plaintext message, and what we do is we write that over k rows. Okay, so a key again is k, that will be chosen, maybe 2 rows, 3 rows, or depending on the length. And the ciphertext is obtained by reading row by row. And that one will do, just quickly demonstrate. Let's say we have some plain text, and for the demo it needs to be a little bit longer. So here's our plaintext message I want to send, and we'll choose a key. I want to encrypt that. I use a key. It doesn't have to be the same as the previous one. Let's use a key. I'm going to use the same key of 3. We'll see why in a moment. So it could be different. It could be 4, 5, 2. There's some limits on it. So to obtain the ciphertext, what we do is we write this plaintext in 3 rows. It doesn't have to be in diagonals, but you'll see it's a little bit easier to read. H-E-L-L-O, hello. Tell me if I spell it wrong. I wrote it in 3 rows. Why? Because I chose a key of 3. And now the ciphertext, I read those rows. The ciphertext from this encryption is H-L-T-E-C-I, the first row, then the second row, and then the third row. So this is a different cipher called the railfan cipher. A very simple cipher for transpositions. This is a transposition cipher because all we're doing is rearranging the letters in the plaintext. The set of letters in the ciphertext is identical to the set in the plaintext. We don't have any new letters in there. So there were 2 L's in the plaintext, there are 2 L's in the ciphertext. So it's just a rearrangement. Whereas with the Caesar cipher, we substitute with other letters, potentially other letters. So that's the difference between substitution and transposition. Two of the simplest ciphers are very insecure. They have a number of weaknesses. But that's not the point. The point is that the 2 operations are demonstrated. How would you break these ciphers? That is, if you're an attacker and you know the ciphertext but you don't know the key, how would you find the plaintext? Maybe starting with the railfan cipher. If you knew the value of the ciphertext, what would you do to try and find the plaintext? You don't know the key. You don't know it's 3 rows. What would you do? Guess what? Guess the key. Okay, so there may be a limited value of keys here. It's actually limited by the length of the plaintext. If you have a very long plaintext, you could, let's say we have a plaintext of millions of letters, a very long document, then the number of keys, there are many possible keys. Maybe you can do better than just guessing the key. So yes, you could guess the key, decrypt, see if you get plaintext that makes sense. If not, try another key. If not, another key. Can you do it better than that? Write a program. What would your program do? Guess the keys. I want to be smarter than guessing the keys. Not necessarily faster, smarter. Well, turns out that you could look for some patterns in the ciphertext based on your knowledge of English and your knowledge that certain characters go together. In English, it's not very often that you have T followed by L in a word. So you could start to look at the expected pairs of letters of the plaintext and the expected frequency of letters, especially when you have very long plaintext. So if you know something about the patterns of letters that you expect in the plaintext, you can actually do analysis, and instead of guessing from all the possible keys, you can try just a few and eventually you'll find the plaintext. This one's not so hard because it's quite small to guess. Similar with the Caesar cipher. Yes, you could try all possible keys. How many possible keys are there with this Caesar cipher? How many keys would you try if you had to try them all? So the Caesar cipher shifts by k positions. What's the largest value of k that we have? 25 or 26 maybe. That is, you can have k as large as you like. 0 positions. Take your plaintext, shift by 0 position means don't shift. The ciphertext and the plaintext will be the same. That's not very good, but it's a possible key. key. If K is 1, shift by 1 position. If it's 2, we did with 3. If it's 26, start with the letter A, shift 26 positions to the right, and you actually come back to the letter A, which is the same as shifting by 0 positions. 27 is the same as shifting by 1 position. So in fact, with the Caesar cipher, there are only 26 possible different keys. So an attacker just has to try all those 26 values. One of them will give them the right plaintext. That's called a brute force attack. But again, there are more intelligent attacks. And if you analyze, especially with long ciphertext, if you analyze the structure of the number of letters, the number of pairs of letters or diagrams, you can quickly do an attack to defeat this cipher. The last thing to demonstrate we will not demonstrate, but say to make ciphers stronger, we saw an example of a substitution cipher and a transposition cipher. Real ciphers in use today don't use those, but they use the same principles of substitutions and transpositions, and what they do is they have multiple steps. They do a substitution, then a transposition, then another substitution, and another transposition. And they in multiple stages, or rounds they're called, such that if they do it enough times, then it's very, very hard, practically impossible, for an attacker to go from the ciphertext and work back and get the plaintext. So that's what a product system does. I will not go through the example, but basically apply the Caesar cipher on your plaintext, and then apply the railfence cipher, mix up the letters, and then apply the Caesar cipher again, and then apply the railfence cipher again, and eventually, after multiple applications, you'll get a ciphertext, and it can be seen that ciphertext is very hard to work back to get the plaintext without guessing the key. And that's the principle that many ciphers are built on today. The intention of those examples is not for you to have to remember those ciphers, but understand some of the basic principles of real ciphers. So we saw something about the attacks that can take place. What does the attacker want to do? They want to find the plaintext. If they only know the ciphertext and the algorithm being used, they want to find the plaintext or the key. Finding the key is often considered better than finding. We assume the attacker knows the ciphertext. They know the algorithm being used. They know if it's a Caesar cipher, if it's a railfence cipher, or something else. And in practice, they usually know other pairs of plaintext ciphertext, but not the key that was encrypted using the same key. That is, the attacker may know that in the past, someone took this plaintext message, they encrypted it with a cipher, with a key, and got this ciphertext. The attacker knows the pair of plaintext and ciphertext, but they don't know the key. And there are ways to get that information. And therefore, the attacker works with that to try and work back and find the plaintext or the key. And there are two approaches, and we sort of saw them in the previous examples. Try every possible key. It's called a brute force attack. That's the dumb approach. It works sometimes, but very easy to defend against by making sure that they need to try many possible keys such that it takes too long. The smart approach from the attacker is to do analysis on the ciphertext, the algorithm, to try and work out what the plaintext or key is. But that requires good knowledge of the algorithm and finding weaknesses in the algorithm. That's hard. We'll see shortly some statistics or performance of attacks on real algorithms with respect to brute force and cryptanalysis. But let's specifically now about symmetric key encryption, which we've mentioned. Symmetric key encryption is commonly used for confidentiality. The same model before. We take our plaintext. I've just introduced some shorthand notation. Plaintext P. We encrypt it with an algorithm, and we take as an input a key K. We get ciphertext. We can write it mathematically. We apply the function E as inputs, the key K and the plaintext P, and as the output we get ciphertext. And then the receiver decrypts that ciphertext using the same key. It's the same value of K here. And the algorithms must be designed that when you decrypt that same ciphertext using the same key, you'll get the original plaintext P. This is called symmetric key encryption because both sides use the same key. Symmetry amongst the key. It's often called a shared secret key or a shared key. Later approach we'll see that they use different keys. The algorithm used for encryption should be good. We say it should be strong. Strong means that if an attacker knows the algorithm, they know the ciphertext, and they even know pairs of plaintext ciphertext, they should not be able to find the plaintext or key within reasonable time. And the other requirement here is that the key is known by both sides, A and B, and is not known by anyone else. If I say it's a secret key and someone else knows it, then it's not secret. We assume no one else knows the key. So, we saw a very quick example of the Caesar cipher and the railfence cipher. They are not used. They are just to show how to do something on paper. What algorithms are used for encryption and decryption in the past and today? That's what the next few slides will list. Just the names of some of the ciphers used, so you're aware of them. One of the first and maybe one of the widely used ciphers in the world was called the Data Encryption Standard, DES, DES. So that was the algorithm for doing the encryption and decryption. Designed in the 1970s, come from IBM and the NSA in the US, and became a standard in the US government and therefore widely used in many different countries. The details of it we're not going to cover, maybe pick up on some important things. It used a key length of of 56 bits. So our real ciphers that we use today are not operating on letters A, B, C, and D, they're operating on binary values. So our ciphers operate on a sequence of binary values, and the keys are measured in bits, so a binary value. So with DES, the effective key length was 56 bits. It was actually 64 bits, but 8 of them were of no relevance to the encryption. And that was an important, a significant limitation of the cipher. You'll see in a moment. The key size was insecure. So DES was earlier and widely used ciphers, but it had a limitation in that the key length was too small, and therefore new ciphers have been developed over time. Before we look at them, let's just simply do an encryption with DES. This is just a summary of the DES algorithm. The point of this picture isn't for you to know how it works, but to show that it's quite complex compared to the Caesar cipher. Move K positions to the right. Well, that's easy. DES involves, very hard to see, but involves 16 rounds. 16, we do something, we do it again, and we do it again 16 times. And each round involves things like, because it's operating on bits, doing more shifts, shifting the bits to the left, doing permutations. So permutation is another word for transposition. Rearranging bits, moving one bit to this position, and the other bit to another position, and doing substitutions. It uses S boxes as a concept. The point is that, even though it's a very complex cipher compared to the others, it uses the same principles of transpositions, substitutions, one after the other, and repeats them all again in the second round, and repeats them all again, and consider it to be a secure design. We cannot go through examples on the board. I'll simply show one using a computer. Let me encrypt a file, just to demonstrate. So the plaintext.message I'm going to encrypt is here. Okay, so it actually finishes at this point. So I've just created a text file. That's our message that we want to encrypt. That's the plaintext that no one else should be able to read. And what I'm going to do is just use some software to encrypt it. We're going to use DES, and actually before we look at that plaintext message, what DES does is it operates on a set of bits at a time. It encrypts a block of bits, and then encrypts the next block of bits in that original plaintext, and it works on 64 bits at a time. DES is uses what's called a block size. So if your plaintext message is 128 bits, DES encrypts the first 64 bits, and then separately encrypts the second 64 bits. If it's not a model of 64, then it can add some padding to make it a model. So the ciphers that are used in practice today use a fixed size block, usually small in terms of 64 bits or 128 bits. How long is our message? Our message is 72 bytes long. DES does not operate on characters, it operates on binary values, on bits. How many bits in this file? 72 bytes, or 72 characters. Well, with ASCII encoding, we represent, in our file system, we represent every character with an 8-bit value. Let me zoom out and try that again, because it wraps around. That's better. So this is the actual file, but in a binary form. The values are not important, but just to make it clear that this is the first 8 bits represent the letter uppercase H. So what DES does is take 64 bits at a time, encrypts it, and then produces ciphertext, and then does it again for the next 64 bits. So let's encrypt using DES, the data encryption standard.